Hello, this is the Exam 2 review for Organic 2 Fall 2021. This review is going to primarily talk about infrared spectroscopy, mass spectrometry, and carbon and hydrogen NMR spectroscopy. So we're going to work through these problems. So you're going to be given a pair of molecules and a spectrum. And so the idea is to figure out which one of these molecules goes with the spectrum in here. So you're going to go ahead and assume that the alkane CC and alkane CH signals are there, even if I don't list them. And so what we'll want to do is want to say, okay, what signals would we expect from here? Okay, well, we would certainly have the alkane CC and then the alkane CH. That would be for both of them. But this one would have a couple of additional signals, right? Because remember, there's a carbon. You'll get a signal from the alkene, as well as the hydrogens that are coming off of the alkene. So the CH is coming off of an alkene. Okay, so if we look at these, right, so we have 1650, and then we also have what, 3050. So the 1650, right, we have a couple of different options, right? We could have, you can have an amide, or you can have an alkene. Well, we don't have an amide functional group in our molecule, right? So it can't be this. The 3050, right? Now that one goes with this alkene CH. So for this one, we're going to have both of these signals. This molecule cannot produce either one of those signals, so it has to be this. Okay. All I'm looking for, you don't necessarily have to do this analysis, you just need to look at here. Now, if it was between this one and, say, this molecule. So this one, again, would have the alkane CC and the alkane CH. However, it would only have this one as well. It cannot produce this one. So it would be able to produce the 1650 peak, but not the 3050 peak. It cannot do this. So if I was giving you these three, it would still be this one. This one can't make that the 3050 peak. So it would be here. What you would see if I would give you these three and it was, say, this one. Okay, well, 1650, well, that's an alkene, right? So that would be for both of them. But what would happen is it would be this one, because this one would have that additional CH peak. Okay, that would require here. So if it was just 1650, so this one would be 1650 only. Well, this one would be 1650 plus the 3050 peak. So you have to be careful about what's there and what's not there. Okay? Now I am going to give you this chart, okay, so you don't have to memorize it, but do be sure to know how to use it. So for this one, how many different signals would you expect in the hydrogen NMR and the carbon-13 NMR spectrum? Okay. So we're looking at sets of signals, and so this is a way of asking how many equivalent hydrogens do you have, and how many sets of equivalent hydrogens and how many equivalent sets of carbons do you have? And so when you're trying to solve something like this, usually the first thing you're going to want to try is to just put in the hydrogens. So we're looking for the hydrogens first. Oops, that's the 3, CH2. These are C's. Here's a CH. Right? Here's a CH. CH. Right? CH. And then obviously that's CH3. Now, these two, if you want to look at these two CH3s first, right, they're different, okay, because this CH3 is bonded directly onto the benzene, while this one is bonded to a CH2. So these will give different signals. Okay. For this CH2, it's the only CH2 in the molecule, so that'll give a signal in the hydrogen. Now the question is, if we're looking at, say, these two hydrogens here. Now, for this one, okay, these two are not equivalent to each other, okay, because this one is near this methyl group, this one is near an ethyl group, and so these two are not the same. However, these two are, okay, so these CHs are equivalent, and you can think about that as if you're holding on to the methyl and ethyl group and spinning the molecule, kind of like if you take a quarter and flick it and have it spin, right? If you flip the ring over, right, the molecule is still going to look the same. So these two are equivalent, and then these two are equivalent here. So we're going to get 1, 2, 3, and then a signal for these two hydrogens and a signal for these two hydrogens. And so we're going to have 1, 2, 3, 4, 5 signals. Now for carbon, let's do this. Let's go ahead and draw it like this. Now don't forget with the, so you're saying like, what, but wait a minute, hold on. This one is part of a double, I forgot to mention this before. This one is part of a double bond, while this one is part of this double bond. Well, remember we can do a, we can write a resonance structure where those double bonds go all the way around. And so a better way of thinking about a benzene is more like this, where the double bonds are smeared all the way around. Okay, so you don't have to worry about with the with the resonance here, because all of these double bonds are smeared. Okay. So for this one, okay, if we're looking at just the carbon NMR, right? So these three carbons here are going to give separate signals for the exact same reason why these hydrogens, their respective hydrogens, are going to give separate signals. Okay. Same goes with these carbons here. So these carbons will give us a signal that's representative of both those two, because those are equivalent. Same goes with these two. Now, what about these two carbons here? Well, they're different, right? Because this carbon has a methyl group hanging off of it, and this one has an ethyl. Since they have different things hanging off of them, well, then they give separate signals. Okay, so we're going to get 1, 2, 3, a fourth one that is representative of these two carbons, a fifth one that goes with these two carbons, and then sixth and seventh, right? So 1, 2, 3, 4, 5, 6, 7. So we're going to get 7 separate carbon signals. Now predict the structure. Okay, so you're going to have a mass, and then you're going to have some sort of functional group. Okay, so remember for a ketone, remember this is a C double bond to O with 2 carbons on either side, with a carbon on either side. Okay. And so that what that means is that our formula, we don't know how many carbons and we don't know how many hydrogens, right? But we do know we have an oxygen, right? Because we need one to make the ketone, right? Because it's C double bond O. All of this is equal to 58. Okay. So we don't know how many carbons, we don't know how many hydrogens, but we do know that that oxygen is going to be contributing 16 to the overall 58. And so we know that the number of carbons plus the number of hydrogens, plus 16 is going to end up being 58, right? So this is the molecular mass of carbon. Right, so with that, and so that, so we know that the carbon bit plus the hydrogen bit is going to equal what, 42? So now we need to guess. So since this is a pretty small number, we're going to go with a small number of carbons. Okay, so if we had 2 carbons in the molecule, right, the maximum number of hydrogens would be, right, so it's this 2n plus 2, right? So it would be 2 times the number of carbons plus 2. That'll give you the maximum number of hydrogens, right, plus 2. So that means this is what? 4, this would be 6. So that means if we had 2 carbons, the maximum number of hydrogens we could have would be 6. So what was this? What would this weigh? Right. So for that, so well, it would be 2 carbons. Each one of those, carbon has a molecular mass of 12, so we have 2 of those, so it's 2, right? And then we have 6 hydrogens. Each one of those weighs 1, right? So we have 24 plus 6, right? So that's it's 30. Okay, we're not quite to that yet. We can't add additional hydrogens to get up to that 42. So what we need to do is instead, we need to come in here and we need to add another carbon, right? So now the max number of hydrogens, right? So 3 hydrogens plus 2, right? So that would be 8. So if we had C3H8, right, we would have 3 carbons. Each one of those is worth 12, right? And we would add 8 hydrogens. Each one of those is worth 1 because that's molecular mass, right? So like that. And so if we do this, it's 36 plus 8. We have 44. So we're a little bit above where we need to be in 42. So the easiest way to get there is to subtract 2 hydrogens, okay? And that will give us a formula, C3H6. Now, well, that's really bad, 6. We can't subtract a carbon, because if we do that, then we would be back up here, and max we could do is 30. But if we subtract 2 hydrogens, then this, if we calculate this out, would be 42. So the final formula is going to be C3H6O. And if 3 carbons, right, each one of those is worth 12, so 36 plus 6, that's 72, or is it 42? And then another 16, that makes it 58. Now, I didn't ask what the formula was. I said predict the structure. Okay, so the easiest way to do this is to come in here and you say, okay, well, let's do a quick DOU, right, just to see if there's any rings or pi bonds, things like that. So 3 times the number of carbons, or excuse me, 2 times the number of carbons, which in this case is 3, plus 2, plus, we don't have any nitrogens, we don't have any halides, but we do have 6 hydrogens, right? So that's 2. So this is going to be 8 minus 6, 2 over 2, 1. Okay. Well, okay, so that means we have a ring or a pi bond. Well, we know we're going to have a pi bond because we have it here to make the ketone, right? And since we have 3 carbons, and the C double bond O has to have a carbon on either side, then our structure is going to end up having to look like this, right? Because if the C double bond O was over here, then it would be an aldehyde, because you'd have a hydrogen over here. For a ketone, you have to have carbons on either side. So the final structure is going to look like this. And the question that I give you is probably going to have more carbons and a different functional group. There may be multiple ways to draw this structure, and that's fine. Just draw it out. It's fine. You're not supposed to read my mind to figure out the exact one that I'm looking for. Here there was only one choice, but there could be multiple ways that you can solve this with the actual structure. The formula, there's only one way, but the structure, there may be multiple ones, and I'll take any of them. So there we go. Okay, so predict the structure. Okay, so for here, this is a carbon and carbon 13. Okay, so the broadband, right? So the first thing you're going to want to do is just take a look here. Say we've got 5 carbons and we have 1, 2, 3, 4, 5 signals. Okay, so that would indicate that there are that there are no equivalent carbons in here. Everybody is, each carbon is, it's unique. Okay, so that's good. And usually what I tell people is like, the first thing to do is just run a quick DOU check to see what to look for. Okay, and so 5 times, right, so it's 2 times the number of carbons, so it's 5 plus 2. There aren't any nitrogens nor halides, but there are 10 oxygens, or 10 hydrogens. Right, so it's 2. So it ends up being 2 over 2, which is 1. So we either have a ring, okay, we either have one ring or one pi bond. We don't know which. Okay. Now, next up, let's look at the depth. Okay. So remember, for depths, right, the depth 90 shows you the CHs. Okay. So we know that this 138 is a CH. The positives, okay, so the depth 135 will show the CHs, the CHs and the CH3s. Okay, we've already assigned this 138 as a CH. Okay, so we know it's not a CH3. If it was down here, we could tell that if it hasn't been assigned as a CH, then the signal must be for a CH3. But in this particular molecule, apparently we don't have any CH3s. The 138 is a CH. These guys here, though, these are all CH2. So the negatives, it's right over here. The negatives show the CH2s. So that means that this one, this one, this one, this one, these are all CH2s. Okay? Because that's what a negative signal in your depth 135 experiment shows, which that these are those signals are going to be negative to indicate that the carbon at that's giving that signal is a CH2. So one of the things I always advocate is to come in here and just do a quick check to make sure we've accounted for everything. Okay, so we have a CH2, right? We have 4 CH2s, right? And then we have, and then the CH. Okay, and if we count all of this up, okay, 2, 4, 6, 8, 9. Okay, so we have all, so see, we have all the carbons accounted for, but we only have 9 hydrogens accounted for. So what are we missing? Missing is an OH. Right? We're basically missing an alcohol group. Right? So because we have, right, the oxygen isn't accounted for yet, and only 9 of the 10 hydrogens are accounted for from our depth experiments. Okay, so we have to be aware of that. Now, next up, we need to look at the shifts, which I think, oops, I don't have. So, if you look on the chart, okay, these guys here, pretty much 50 or 60, like 50 or below, these are just regular alkane peaks. Okay. This one here is typically either a carbon with an oxygen or carbon with a halide on it. Okay. Well, we don't have any halides, right? So it needs to have the oxygen on it. Okay. These guys here in this 100 to 150 region. These are alkenes. Those carbons show up there. And so what we know is that we have a CH2, right, bonded to a CH, right? So this is one side of the carbon, and that's of the alkene, and this is the other. Okay. but this also gets us our 1 DOU, right? We know that it's a double bond. Okay. So what we know about this is that we have a carbon. Right? We have on this side we have two carbon. We have a double bond, and then on this side we have one carbon, right? Because it's a CH. Notice how we don't have all 4 bonds over here are accounted for. So that must mean that this is at the end of the chain. Okay, because we can't add anything more onto this carbon. We only have a bond over here that's left. Okay? And so that must mean that this must be the end, and things must extend over here. And so if we look at this one, right, so CH2, so that must mean, right, we have 3 other CH2s that we can't account for. So CH2, right, CH2, right, and CH2. So we have to have these extended out, and it can't be a ring. They're not, they're separate signals, so they're not equivalent to each other, and so that's pretty much the only way we can do this. Okay, CH2, CH2, CH2. Now remember we had this OH that we had to account for. Well, we can't put it on the red or the green one because there's no space, right? They already have their 4 bonds accounted for. So the only place that we could put it, right, would be right here. So here's our structure here. Okay, and this would make sense, right? Because it needs to be next to the OH. So these two would be these two right here. This one would be here. This one. These two would be those right there. You don't have to identify which one is which. I'm just looking for the structure, stuff like that. But you know, it's good to double check to make sure things make sense. Okay, so for this one here, so predict the structure. So for this one, right, again, the first thing we're going to want to do, notice how we have 10 carbons and we only have 1, 2, 3, 4, 5, 6 signals. So there's going to be either some equivalence or there's going to be some carbons without hydrogens on it, or both. Okay, but the first thing to do is to run a quick DOU check. Right, so 2 times the number of carbons, so plus 2. We don't have any nitrogens, nor do we have halides, but we do have 14 hydrogens. Right, so it's what, 22, so it's 22 minus 14. 8 over 2, so it's 4. Now, a good rule of thumb is that if you have a DOU of 4 or more, you probably have a benzene, right? You have a ring in those 3 pi bonds, okay? 95% or more of the time, it's going to be a benzene, okay? Kind of fun when it's not, but it's probably going to be the easiest things. So that's a good place to start. Okay, is probably be aware that it's a benzene. Okay, so the next place I usually start is right in here. Okay, is to look at the integrations, and for here we're going to have a CH3. Right here we're going to have a CH2. Right, because there's 2 hydrogens. CH3, CH2. CH2 and a CH2. Okay. Now if we look at the splitting, okay, it's a triplet, right? So remember this is n plus 1 equals this, right? So what plus 1 equals 3? Well, that must mean it's next to a CH2. For this one, a triplet of quartets, that just means on one side we've got it's getting split into a triplet. So that must mean that there's a CH2 on one side, and on the other side it would be the equivalent of getting split into their signal into a quartet. So that means that there's a CH3. That's all that means. So we've got something that splits to a triplet on one side, and on the other side we've got something that splits into a quartet. So it would be a CH3. A singlet just means that there's just a carbon, right, especially since it's a hydrocarbon, carbon with no hydrogens. Here again it's a triplet, so this must be a CH2. Here it's a doublet, so each one of these is a CH. Okay. Now the thing to do is I usually come in here and I look at the splitting, or at the chemical shifts. So these guys here, okay, these are just normal alkane peaks. Okay. The 2s, okay, I don't have this on here. There's a whole bunch of things it could be. Okay, it could be a CH, a CH next to a benzene. Well, that could be it. Right? It could be next to an alkene. Well, that's fine. But it's not going to be next to a C double bond O. We know that because there is no oxygen in there, or sulfur, things like that. So we can start narrowing it down to what it's not. Okay? And the most likely scenario is that it's a CH next to a benzene. Right? Because we have the 4 DOUs. If it was, say, a 1 DOU or 2 DOUs, then it couldn't be next to a benzene, and so since we don't have an oxygen, it can't be next to a C double bond O. It would need to be next to an alkene. But since we have enough carbons and we have enough DOUs to this, it's probably going to be a CH next to a benzene. Now these guys here, these are the benzene hydrogens, right? So you have a benzene with a hydrogen coming off. Those are the ones that are directly opposite of them. Okay, so this makes sense. So these make sense in light of this, because we have hydrogens right in the 7 region. That's the only thing that's there. Okay, but these are going to be next to the benzene. Okay, so how are the benzenes oriented? Okay, so for here, there's 3 possible ways that you could have it. Okay, if you're going to have 2 things, right? Because we know we have 2 things hanging directly off of these. Right, because we have 2 separate signals. Okay, so you can have them, right? You can have them next to each other, right? And so that means the hydrogens are like this. You can, R. You can have the signals. Well, let me get this different color. You can have the R groups like this, and that would have the hydrogens like this. Or you could have this structure, this orientation, where you have one group here and one group here. And so for that one, you would have the hydrogens in this configuration. Right? And we know this too. The other thing is there's 4 hydrogens total, right? So there's 4 hydrogens on the benzene ring. Okay, so how do we have these how do we have these? Okay, well, for each one, assuming that these R groups are different, which we know they are because they're giving separate signals, right? One's a CH3 and one's a CH, or one's a CH3 and one's a CH2. So these are going to be separate. In this case, all 4 of these are going to be non-equivalent. So we're going to get 4 signals from here. Okay? We only have 2. So it's not this. Okay, so it can't be this orientation. Same thing with this one. Notice how we've got this hydrogen here. That would be a singlet. We would have a singlet in that 7 region. We don't have that. Okay, we'd also have these 4 signals here, or these 3 signals, which would give additional, peaks, whatever it is. But here we'd have 4 signals and one of them would be a singlet. We don't have that. Okay, so it can't be this. So the only orientation it could be is this. And the reason why, and the reason why it can be, right, is because remember these are equivalent, and these are equivalent. Okay, now this is a little weird because, yeah, these 2 are equivalent, but what's happening is this is splitting this one, and then this one is splitting this one. And these splittings, because the carbons are so far apart, they only split as a doublet. Okay, so this doublet of doublets in this 7 region is very indicative of this what's called pair orientation. Okay, because we have these two signals only, which allow the orientation to have these 2 be equivalent and those 2 be equivalent. Okay, so it has to be like this. And so what the structure needs to be is it needs to be like this. So we have the benzene, right? We have hydrogens here, right? Because this way that they could be equivalent, okay? And what we have right next to the benzene is we have we have this CH3, right, which is this, right, 2.46 signal, and then here we have this a CH2, right, which is this 2.66 signal, right? Now, what do we have next to the CH2? Well, we have another CH2. Okay. And then this one you can say is, that's probably this one here, right? We've got a CH2 in here, but we have this CH3 here, right? So that's probably going to be the CH3 here, right? So this one is probably the 0.93 signal, and this is the 1.62 signal, right? Again, you don't have to account for this. I'm just looking for the structure, but this is how you get these, right? And these red hydrogens here are going to be these two. It doesn't really matter which one is which. And so that's how this works out. Okay, we have a CH2, right, with a CH2 next to it. We have a CH3, right, with just a carbon next to it. It doesn't have any hydrogens on it. This carbon here is this 162, right? So we have a CH2 on one side, a CH3 on the other. And then the 0.931, it just has a CH2 next to it. So that's the structure. So there you go. Okay, so I'm going to start clicking through these slides and sort of point out where the purple notations are. Okay. So I'm going to give you a similar chart to this. Okay, so you don't need to memorize this. Okay. So you do need to know this. We talked about this earlier in the slides, right? So if you have signals, which one of these is it? Is it? Right? So here the 2150, right? This one is the right? This is going to be the 2150 is, well, is this right here? Right? This 2950, right, is going to be, well, it could be the alkyne, right? Right, so for the alkane CH, right? But what we don't have is we don't have this. Okay, so notice how this one would have an alkyne CH peak, which would be at 3300. We don't have that one here, right? Because each one of these carbons, right, it's next to a CH3. Neither one of those has an H coming off of it. Okay, and so what we would get is it's this one, because there's no alkyne CH peak. So it's here. So you need to know that, know how to do that. Okay. For the mass spectrometry, it's there to determine the molecular formula for the molecule. And one of the things we have to do is we have to give it a charge, and specifically we have to give it a positive charge. Now we can do that with electron bombardment by knocking out an electron. So the molecule has one fewer electron than it does total protons. Okay, so it has an overall positive charge. Okay. Now what we get out is the molecular ion is designated as N+. Now, if you see these small quantities of very small peaks that are that are next to the main the main parent ion, okay, what's happening is you have these they're caused by the isotopes. Okay, these ones with these extra high neutrons in them. Okay, these small amounts. Now some of these are very diagnostic, right? For the bromine, right? It's 50% of this isotope and 50% of this isotope just naturally. So half the molecules, so half of these molecules will have a 37, which gives, if you add it up, would be a 158. The other half has a bromine with an 81. Okay, so you add it up, and that would be 258, depending on which. So you would give a lot of different signals. So 2 peaks, right? An M and an M plus 2 peaks that are equal in size. That's very indicative of a bromine. A chlorine is mostly the smaller one, but it's about a quarter of it. Of these are this M plus 2, so it's a 3 to 1, so 75-25%. Okay, so again, this is a fingerprint for having a chlorine on there. Now, one of the quirky things about nitrogens is that if you have an odd number of nitrogens, it's the only one where you would get the M plus being an odd number. Okay, so if you see a molecule that, like, have a mass of 31, you know, oh, that means I've got an M plus is 31. Wow, that must mean I have a nitrogen in there. Okay. Now, if you have even numbers of nitrogens, right? 2 odds. If you add them together, would give an even. But if you have an odd mass, that means you have an odd odd number of nitrogens. So again, don't forget to. I'm going to give you this formula, but you remember, know how to use it. Okay. I'm going to give you this one as well. Right. So know how to use this. Know how to do this, right? We talked about this earlier. Now there are some softer ionization methods. Okay, they're what are called electrospray ionization, or sometimes abbreviated as ESI. There's also MALDI, matrix-assisted. I think that's matrix-assisted laser desorption ionization. Both of those worked by, again, it's very similar concepts. So if we want to give the molecule a plus charge, but we're going to do it in this way by adding an H plus. So we have to account for the extra mass that we're putting on there. Not only are we giving a plus charge, but we're also adding 1. Okay, and so so if your sample was 1,000, then 1,000 molecular weight, and you did this for electrospray, what you'd be looking for would be a sample, a signal at 1,001. Okay? Now the nice thing about this is that there's no fragmentation. And you can do much, really big, large samples. So 1,000 molecular weight, 1,000 Daltons, or 100 kilodaltons. Okay. Now for NMR, okay, we're going to be using radio waves to determine how these atoms are oriented in space. Okay, and we're going to be shining these radio waves in there and seeing how they interact. But we're going to be putting the sample in this giant magnet. Okay, and we're going to take advantage of the fact that some of the nuclei have magnetic. Some of these isotopes have magnetic nuclei. Okay, and I can determine that is if it has an odd number of protons or an odd number of neutrons. It can have both. It can have odds of both. With that, but if it satisfies at least one of these criteria, it's going to have a magnetic nucleus, and so we'll be able to see it within an NMR. So hydrogen, right? So that has an odd number of protons. So yeah, it's magnetic. Same with fluorine 19, right? It has nine protons. Okay, so it's also magnetic. But if something like oxygen 16, it has even numbers of protons and neutrons, so it's going to be blind to a magnetic nucleus, right? So if we had something like oxygen 17, or excuse me, actually I take that back, something like oxygen 15, okay, we'd still have 8 protons, but we would have 7 neutrons, and so this would be a yes here, because we would have an odd number of neutrons. Again, you can have an odd number of neutrons and an odd number of protons, and again, it would be magnetic. You just have to have at least one of these to be magnetic. Okay. Now you do need to know how to determine equivalence, and we talked about that earlier, where we're looking at how many signals would we get. That's really what we're asking is equivalence for hydrogen. How many sets of equivalent hydrogens do we have, and how many sets of equivalent carbons do we have? So that's what this is. But remember, with the double bond, you can't get free rotation around here, and so if you have a sample like, so you have to be really careful around alkene hydrogens, right? Because if you have these two here, because you can't get free rotation, these would give two different signals, even though they're on the same carbons. They can also split each other, right? Because remember, this carbon is feeling this chlorine, but this hydrogen is feeling this hydrogen here, so they're in different chemical environments. So this molecule here would actually give three distinct hydrogen signals. So be careful on that. Now, one of the things that happens is the NMR is really slow. Okay, so if we want to slow it down, okay, if it's going back and forth really fast, okay, on timescales much faster than what the detector can pick up, what you need to do is you can't speed up the detector because you're using, because it's the limitation of the radio waves, but you can slow down the molecule. Okay, and so the way you do that is you cool the sample. And so for this one, if you were looking at, being able to detect these two, right, they are in different orientations, right? So they are actually non-equivalent to each other. In this case, if they're in this orientation or this orientation, right? So one's axial, one's equatorial. But remember, they're flipping back and forth very quickly. But if we cool it down, that the chair flip is slowed down to the point where we can actually detect the two different ones. Okay, so as you cool it down, you'll be able to slow the chair flip down to where the NMR can pick it up. Now, the chemical shifts. Okay, so this is where along this line here you would see the peak itself. That's going to give a lot of information about the neighborhood. Just like with IR, right, where the signal shows up is going to tell you a lot of information about the molecule. Okay, and all these peaks are relative to tetramethylsilane. Okay, so we're going to set that at 0. Okay, and so it's how far shifted away from TMS is it? So it's called a chemical shift. So the reason why we do this is because the silicon here moves it out of the way. If it was a carbon in the center, okay, its signal would be probably in amongst all the other alkanes, okay, and so you wouldn't know which one's your signal and which one's the reference signal. By putting that silicon there, it actually shifts it a little bit farther upfield to get it out of the way from all the normal alkane peaks. So that's one of the nice things about that as a reference. Okay. So what they're doing is the signals are seeing that the differences in how they're feeling the magnetic field. Okay, I'm going to give you a chart like this for the exam. So again, you don't need to memorize it, but you need to know how to use it. Okay. Now, one of the things about this, and this is mostly with the homework, is that these aren't written in stone. Okay, these are kind of generally where things show up, but it's not a hard break here. Sometimes if you have sometimes alkanes can shift, say, into this region, if they are if they're near near, say, electronegative atoms or things or double bonds, things like that. If they're by a couple of them, they can become additive and they can shift the signal up here. And so do be careful about that. Now on the test, I'm going to make sure it's in those boxes, but for the homework, it's popped up a couple times where it's shifted out of the box and it's confused some of the students. So do be careful that this is a guide. It's not it's not exact. Okay. Now, one of the things about the chemical shifts is that you have NMRs with different magnetic fields. Okay. However, the computer is able to compensate for that. Okay, and so no matter which type of NMR you're going to get in, if you have a signal, say at this 5.4, okay, so if you have a signal here, notice how all of them are at 5.4, whether it's 400 megahertz or 300 megahertz, it's at the same point. Okay, so with that, and so if you have a signal here versus here, it's still gonna be a triplet. It's still gonna be a triplet at 5.4, no matter which NMR you do this. What the difference is the fact that the resolution that you can see. Okay, so these are actually all, these two triplets here, they're just all smashed together. Okay, by going to a higher field strength. Okay, they're still at the same positions. It's just you're able to get a lot more detail if you zoom in. Okay, they resolve themselves, but they're still going to be the same signals. Okay, so that's the nice thing is if you run it at a 300, run it at a 900, those peaks are still going to be where they're supposed to. Now, things like electronegative atoms can cause that signal to shift further downfield to a higher number, so you have to be careful. Things like double bonds can also do that. Okay. Now, the integration of the signals. So the area underneath the curve is going to tell you how many hydrogens there are. Okay, so the area underneath here, and it's usually either given in a couple of different ways. They just tell you outright. Okay, but it's also sometimes given as this sort of this little signal here, and what you need to do is the height of this right here relative to that right there is going to tell you that there is the relative amount of hydrogens there are for each peak. Okay, so this one is a third of this height here, so that means this this peak is representative of a third fewer hydrogens. Okay, so in this case, if this one's worth three hydrogens, this could be 9. Okay, so it's that you're looking at that ratio. That's really what it's showing. Okay, so you have to be careful because you have to look at those integration ratios. So if you have take a spectrum and it has 3 signals and the integration is 1 to 3 to 6, okay, that makes sense because we have 10 carbons, we can account for all 10. If we have a different molecule and it gets 3 signals, right, but we have 16 hydrogens, well, we only have 3 peaks and it's 1.5, 2.5, 4. Well, that doesn't make any sense because what the heck is a half a hydrogen, right? So what you can do is these are all relative ratios. Okay, so just like 2/4 is the same ratio as 1/2, right? As long as you multiply everything by the same thing, you're fine. So you can multiply everything by 2 and get 3 to 5 to 8. Here's our 16 hydrogens that we can account for here. Okay, so sometimes if you see a half a hydrogen, you have to multiply everything by 2, and that'll get the proper ratio. Okay. So the integration tells you how many hydrogens are on that signal, or associated with that signal. How it's split into its different forms will tell you how many neighboring hydrogens there are, and it's this neighbors plus 1, right? So it's neighboring hydrogens, right, plus 1. And that'll tell you what it gets into, right? So if you don't have any neighboring hydrogens, right? So the n plus 1, so 0 plus 1, you would get just a single peak, and that we call that a singlet. If you have one neighboring hydrogen, right, it'd be 1 plus 1, so you would have 2. It would be split into 2 peaks, and we call that a doublet. Two neighbors, it would be a right. 2 plus 1, it'd be 3. So we call that a triplet, a quartet, quintet. And keep going down, and sometimes you see this multiplet, and that just means everything's smashed together, and it's a mess. Okay, so just be aware. Okay. So again, chemically equivalent hydrogens, they don't split. Okay, they don't split each other. Yeah, so you need to know how to do this, right? So this is a doublet, right? right? So there's 2. So that must mean that there's, right, plus 1, right? So what plus 1 equals 2? Must be 1 neighbor. Here it's 1, 2, 3, 4, 5. So this is a quintet. So what plus 1 equals 5? Well, that must be 4, right? Because there's 1, 2, 3, 4, 5 peaks. For here, there's just 1, right? So this is a singlet. So that must have, it must not have any neighbors to it. Now, how can you have four carbons on a or 4 hydrogens on a carbon? Well, what's happening is this is probably 2 CH2s that are equivalent to each other. So if you had a CH2, two CH2, and say bromines, right? These hydrogens here, these hydrogens here would act like a CH4 group, okay? because they're equivalent, and so this one would be a quintet. Okay. Because it would have 4 neighboring equivalent hydrogens. Okay. So that's how that works. So again, chemically equivalent hydrogens do not split each other. Now, coupling constants, for those, the gap between this gap here and this gap here will tell you, this gap here, here, and here, will tell you which signals go with what. Okay, so things that are equivalent, have equivalent gaps here, that means that these 2 signals go together. These have, again, equivalent gaps between these peaks here. Okay? So that means these 2 signals must be splitting each other. The hydrogens from these signals are splitting. So that helps to tell you what's next to what. It's that extra data. We're not going to deal much with coupling constants, but but it's something to be aware of. Why it's a J, I have no idea. But it's J is equal to, that, the coupling constant. Now, you can have these complex splitting patterns. Okay, so so if you have, let's see if I can show you this. Okay, so if you look at, say, this, right, if we're going to be looking at this signal here, what's happening is on this side, right, there's this CH. Okay, so it's 1 neighbor. So that means that this side is going to be split into a doublet. Oop. On this side, right, you've got a CH2. So that means it's the 2 plus 1, right? So that's going to be a triplet. Okay, so that means the signal for number 2 is going to be, it's either going to be a triplet of doublets or a doublet of triplets. It doesn't really matter which one. Or, okay, this is what a triplet of doublets is, right? So there's 3 doublets, doublet, 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 and there's 3 of them. Okay, so that's what it looks like. But all this is saying is that when you have something like a triplet of doublets, it's just saying, like, on one side you've got something that causes a triplet. On the other side you have something that causes a doublet. That's all that matters. That's all that matters, right? So this causes the doublet, this causes the triplet. So you just look at it one at a time. That's all that means. Okay, so while it's really crazy, it's not as bad as you might think. Okay, and I'm going to write it out: triplet of doublets, or something, or doublet of doublets, or triplet of quartets, or whatever. Some of that. So, and it doesn't really matter which order they're in. It just means one on one side, one on the other. Okay. Now, again, you're going to need to know how to do this problem solving. Okay. So, know how to do this. We did this earlier in the slides. Okay. So we kind of, we've walked through this before. Now, one of the things about carbon NMR, okay, is that carbon-12, right, it has 6 protons, 6 neutrons, so it is not magnetic. So what we're looking for is we're really looking at only the carbon-13. The carbon-14, carbon-12, those are all going to be invisible to the NMR. We're only looking at that small, like 1.1% of the carbon signal. So 98.9% of the sample is going to be invisible. Okay, and so because of that, because this carbon-13 signal is so low, we need to get a lot of signals. Okay, we may need 10,000 different signals and then when we average that out, okay, we can get rid of any noise, any random noise, because over thousands of signals, right, so, or thousands of readings, eventually it's going to go to everything's going to go to 0 except where the actual signal is. Those are always going to be additive, so those will always build up a little bit by little bit by little bit by little bit for each scan. Okay, but then there's also no splitting, okay, which is nice. Again, know how to do this, right? We talked about this before for equivalence for carbon versus hydrogen. So don't forget about this. Again, I'm going to give you this chart, okay, so know how to use it. Also, the integration is meaningless. Okay, so that because the abundance is so low, it's really more of how efficiently the signal comes out, and that doesn't necessarily is not necessarily reflective of how many carbons there are in the signal. Okay. Now, to get more information about this, we're going to run a series of experiments. So you actually run 3 experiments in here. The broadband, that's the normal one. That shows you all of the carbon atoms, okay, that are in the molecule. What you then do is you then run the depth 90. So that's going to give you another set of peaks, and these peaks here, only the CH peaks will show up. So we can assign these peaks as being CHs. Okay? And then you run a third experiment where you run an experiment called depth 135. And for this one, if you get a signal here, a positive signal, that means it's either a CH or a CH3, right? Well, we've already established that these are CH3, so that must mean this one is a CH, or CH, right? So these are all CHs because the depth 90 already showed that, right? We were already able to assign this as CHs. So that must mean we weren't able to assign this one, so this must be a CH3. If it was a CH, we'd see it in the depth 90. Since we can't, then it must be a CH3. These negative signals here, and I've always thought these were a little freaky, stuff like that, but the negative signals, these are indicative of CH2s. Okay, so we actually have three different reads, 3 different experiments. Okay, and then that allows you to figure out what the if it's and lastly, if it's not in either one of those depth experiments, then it's a carbon that does not have any hydrogens directly attached to it. Okay. So again, know how to do these. We talked about that earlier. Okay. Good luck.